Hello everyone. My students in my dynamics class asked me to create a video in which I solve some sample problems from their textbook, which is Bedford and Fowler Engineering Mechanics Dynamics for them for their upcoming midterm exam. And I said, you know what, let me solve this in a video and share it with the rest of you. If you have an upcoming exam in dynamics, maybe watching my video going through 5 different problems of particle kinematics and kinetics might be useful to you. So let's get started. The first problem is here you have this particle P or object P, which is like a small knob attached to a slider that moves inside this semicircular slot, and also this slider P is on this horizontal bar which is attached to this vertical slider, and that can also go up and down. Okay, so while the motion of P is limited to the semicircle, the Y motion of P you can control by moving this slider and the bar, and of course the slider P up and down. So the Y is completely under your control, but not the X. The X, which is this distance, that is not under your control, and it's controlled indirectly through the slot. So at the specific moment, Y is 100 mil, Y dot is 200 mils per second, and Y double dot is 0. So you are moving this slider at a constant speed of 200 mils upward, and you are at location of Y equal 100. The radius of the semicircle, which is centered at origin, if you would like to call it origin, is basically 300 millimeters. Okay, so these are your axes. And now what is it that you need to find? So this is particle kinematics only, because you need to find the velocity and the acceleration of point P in terms of the normal and tangential components. So here you have to use the T and B, or path coordinate here, and you have to find velocity and acceleration in terms of those. So here we have to show the frame. So let's say it's here at the moment, and this is that Y of 100. So you have the tangential component of motion, which is tangent to the path at that point. So this is your ET. And then EN is, of course, in the radial direction toward the center. So this is your EN. And B is perpendicular to the board here, right? Or the monitor outside, which we don't need to focus on that. So it says write velocity of the particle V in terms of its tangential and normal components. So it is going to be something times ET plus something times EN. And then acceleration also should be written as something times ET plus something times EN. So decompose these two vectors along ET and EN and give me the components. If instead it says in terms of the Cartesian components, then instead you have to write it in terms of I and J. But here you see the problem is specifically asking for normal and tangential. Now, right off the bat, we know that the velocity in the NT coordinate is only along the T direction. Velocity will never have any normal component. So this guy right off the bat is 0. We know that. This one is just the speed V. This one here, the tangential component, is V dot, the time derivative of the speed. And this one is V squared over rho, right? These are those formulas that we know from particle kinematics. So in order to fill here, what we need to find is V at that moment, and then v dot, and then a rho. Now in this case, rho is easy. Rho is the same as r. Okay, this is a circular motion also. And in circular motion, rho, the radius of curvature, is a constant, and it's just 300 mils. So rho is good. So what we need to find is v and v dot. But the thing is, here everything is given, if you look, in terms of y, y dot, y double dot, and the relation between x and y. And what relation is that? That comes from the semicircular, the quarter circle, right? You know, in general, if that was a circle, the equation, the relation between x and y is simply what? It is x squared plus y squared equals what? Equals r squared. Right? That's the equation of the arc. And clearly here, if I want to know x at any point, all I need is this r is 300. If I plug in y of 100, then I can find x, let's say. But what I need is v and v dot, okay? And again, since the information is given in Cartesian, so I have to find v through Cartesian, and v, if you remember the speed in Cartesian coordinate, is basically what? It's the square root of x dot squared plus y dot squared. So what I need to find is x dot and y dot. And how do I do that? Well, all I need is to take time derivative out of this governing equation between x and y. If I take time derivative out of this, here pay attention that you have to apply the chain rule, because you are not taking derivative of x squared with respect to x, so it's 2x. You are taking derivative with respect to time. So the derivative of x squared with respect to time becomes 2x, but times x dot. Okay, remember, this is d of x squared over dt, which you cannot do, so you do dx squared over dx times dx times dt. You apply a chain rule, right? This is the 2x, and this is the x dot. Okay, so please pay attention to what you're doing. The same thing applies for the other term. The other term will also becomes 2y dot equals 0. Why 0? Because r squared is simply a constant. It doesn't have time derivative. And now you see that if I want to calculate x dot, given that I know y dot, remember that y dot is 200 mils, right? So this guy is positive 200 mils per second. And y itself is 100 mils. So if I want to find this x dot, so I can plug it here, because y dot is given. If I want to find this x dot, I have to find it through this equation. And it's always a good idea to write in a nice way so somebody can follow. So this original equation, I call it equation 1. And this time derivative version of that, I call it equation 2. Now, clearly, if I want x dot out of equation 2, I also need to know x at that location. And to find x, I need to use equation 1. So from equation 1, if I plug in y of 100, right, and let me clean this portion so we can write a little bit nicer. So if you plug in y of 100 into equation 1, that gives you x. And if you solve for x, you are going to get 283 mils. If you round it to the nearest whole number. Now this goes here, and you can find x dot. And if you find x dot, your number is going to be negative 70.7 millimeters per second. You see, now I have x dot. So it can go here. And y dot I already had, that was 100. From here, I should be able to solve for what? Solve for v at that moment, the speed. So if I bring it down here, this is going to be square root of that negative 70.7 squared plus 100 squared. Okay, and you should get 212 millimeters per second. So that goes right here. Of course, with units of mils per second, not meters per second. So the first part is done, this portion. We wrote the velocity of the particle in terms of what? T and n. Now, one thing before I move on is, does this negative sign make sense here? Absolutely, because if you remember, the speed of the particle is only in the t direction, so this is that speed or the velocity. And if you look at it, it has a negative x component and a positive y component, right? So y dot is positive, x dot is negative, and it should be. Okay, because it's moving to the top and to the left. So that absolutely does make sense. Always do a sanity check and make sure that whatever you found does actually make sense. Okay, so we got the first one. Now we need to find what? We need to find the second one. Now, in order to find the second one, we need v dot. We need the time derivative of the speed, and remember that the second component en is already taken care of because I know v, that's 212, and I know rho, that is 300. So I should be able to calculate this normal component. The only component you need to find is v dot. Well, how would you find v dot? For that, you need to take a time derivative out of this. Okay, if you want, can take time derivative out of that, and I would like to call this velocity relation 3 or equation 3, and if I take time derivative, I'll get v dot, and if you know how to take a square root, the square root time derivative is the time derivative of under the square root over 2 square root. So it is like this. And time derivative of x dot squared, as you know, it's 2x dot times x double dot. Again, here I'm applying the chain rule. And y dot is 2y dot y double dot. So this is your v dot that you needed. And you can get rid of these 2's. So in order to find v dot, you need x and x dot. You need x dot and y dot and x double dot and y double dot. And x dot and y dot are already taken care of. Y double dot is 0, so that makes life a little bit easier. So the only thing you need to still find is x double dot. You need to find x double dot before you can calculate v dot, and for that, you have to take time derivative out of what? Out of equation 2. If you look at equation 2, this is a time equation that is based on time. And if you take a time derivative out of this one, clearly you'll see that here there is a product, and you can get rid of 2 out of both sides. So derivative of x dot is a product. It's derivative of x times x dot. Derivative of x time derivative is x dot times x dot. You get x dot squared. And then plus x times derivative of x dot, which is x double dot. So that's the first term. And then plus the second term, which is very similar, equals 0. So that is going to be y dot squared plus y double dot. And now in this relation 4, if you would call, everything is known except for x double dot. Everything else is known. So if you plug in the numbers here, knowing that also y double dot is 0, then you should be able to solve for x double dot, which is going to be basically negative 159.1 millimeters per second squared. There we go. You got your x double dot. So now you can plug it here, and that should give you what? Your v dot, which basically, if you solve for v dot, this is going to be 53.0 mils per second squared. So that is your first component here, 53. And this guy, if you simplify and calculate the number, if you calculate the number for this is going to be basically 150. Here. And the unit for it is, of course, millimeters per second squared. Right? Done. So this is your what? This is your final answer. You could write both velocity and acceleration in terms of n and t, or normal and tangential components. If somebody says write it in terms of Cartesian, then clearly this is going to be x dot instead. This is going to be y dot. This is going to be x double dot. This is going to be y double dot. And guess what? You have all of those numbers. This is x dot. This is x double dot right here. And then y dot and y double dot are also provided here. So you can also write it in terms of what? In terms of the Cartesian coordinates as well. And the result is the same. It's the same vector. It's the same acceleration vector, which has a t component and one n component here, right? If you look here, this v dot is actually a positive number, because you see x double dot is negative and x dot is negative. So the v dot is going to be a positive number. So your acceleration is going to be something like this, with a positive n component and a positive t component. Okay? So that is the first problem. Let's jump to the second problem, as we have a bunch of problems to solve. So that was kinematics of particles. The next problem is here, again, kinematics of particles, but relative motion, which is an interesting problem. So here you have the river, and the river has a flow of 3 meters per second north, and you want to travel in a straight line from point C to point D in a boat. The speed of the boat relative to water is 10 meters per second, and you want to know in which direction you should point the boat and how long does it take to do the crossing. So your goal is, with respect to a frame that is attached to the ground, you want to directly go from C to D. But you know that if you start your boat here at point C and try to basically steer from C to D and basically paddle, you're not going to end up at D. Why? Because although you have the velocity in this direction, that is velocity of boat with respect to water, you have to add that to the velocity of water with respect to the ground to get velocity of boat with respect to the ground. So you have to add that 3 meters per second to your vector. And so the sum of these two vectors is going to be a little bit more upward. So you are going to probably end up here, because the water is going to carry you a little bit further north. So if you really want to end up at D, you should aim lower. You should aim probably here at this point D prime. So that velocity added to that 3 meters hopefully end up with a vector that is exactly going from C to D. So we need to find the location of D prime, or this angle theta that you should aim for with respect to the east-north, and also what the time, measure the time that it takes to do the crossing. So how do we do that? And this is relative motion. So clearly in relative motion, I can say that velocity of the boat with respect to the ground, and I use B and G for boat and ground, is equal to velocity of the boat with respect to water, I use W for water, plus velocity of the water with respect to the ground, right? This is the basic of relative velocity. If your basically the observer, the object in the middle, which in this case is water, is just translating, which it does. Okay, so the first problem is, what is the angle that I should aim for? So I should aim for this angle theta, and hopefully when I add that to the 3 meters, my actual velocity of boat with respect to the ground will be in this direction, right? So let's see from each one of these vectors, what is it that we know and what is it that we don't know. And here we use the traditional xy to represent the east and the north. So velocity of the water with respect to the ground is clear. That's 3 and it is upward, so this guy is 3 times j. Okay, what about the velocity of the boat with respect to water? What do we know about that? Well, clearly the magnitude of it is given to us. That's 10 meters per second, and it's along this red line with angle theta. So this guy is going to be 10 times cosine theta in the I direction plus sine theta in the j direction. And what do I know about velocity of the boat with respect to the ground? Well, I don't know how fast it is, but I know it's along this green line, right? So if I want this, I can write this as velocity of the boat with respect to the ground, the magnitude of it, which I don't know, times what? Cosine of the angle of the green line, which is alpha, if I call it, in the I direction, right? So let's write it, cosine of alpha in the I direction, plus sine of alpha in the j direction, okay? So now, if you look, clearly your v of bg, the magnitude of this vector, is unknown, as well as this angle theta is unknown. But alpha is known because tangent of alpha is clearly, you can calculate that, right? Tangent of alpha is 400 over 500. And if that's the case, you can find alpha and then you can find cosine and sine of alpha. So these two are basically known numbers. And if you look now, you have two vectors, one on the left, one on the right, and the right is the summation of these two vectors. And clearly two vectors are equal if the I components are equal, the coefficient of the i's and the coefficient of the j's. And if we do that, what do we get? On the left, we have VBG cosine alpha for I. On the right, we have 10 cosine theta for I. For the left, we have what? We have VBG sine alpha for J. For the right side, we have 10 sine theta plus 3. Okay? Basically, these two equations. And now, I don't care about VBG for now. I care about theta. So I need to get rid of VBG between equations 1 and 2. And the simplest way to do it is to divide 2 by 1. So the VBGs would cancel, and then sine alpha over cosine alpha, you get tangent of alpha for which you have a number. So here I'm going to divide 2 by 1, and that gives you what? That gives you that 10 sine of theta plus 3 over 10 cosine of theta equals 4 over 5. And now if you cross multiply and bring everything to the same side, you will get 50 sine theta plus or minus 40 cosine theta. Okay, and you can take that number to the other side. This is equal to negative 15. So this is the equation that you need to solve. Now this is what we call a transcendental equation, and the solution for it involves several different ways. One is you can write a sine of theta plus b cosine theta as basically square root of a squared plus b squared times sine of theta plus tangent inverse of a over b. If you write it, you can write this as something like that, where this portion is a number and that portion is a number. And when that is equal to negative 15, you divide both sides by that square root. You take a sine inverse, and then you subtract that tangent inverse of a over b, which is a number. That gives you theta. That's one way to do it. The other way is to use half angle, tangent of half angle. So you can say that sine of theta equals 2 tangent of half angle over 1 plus tangent squared of half angle, and cosine theta is 1 minus tangent squared half angle over 1 plus tangent squared half angle. And if you plug them up there, then you get an equation that is a quadratic equation in terms of tangent of half angle. Then you take arctangent multiplied by 2, and that gives you an angle. So there are two ways that you can solve that transcendental equation, and if you use any of them, the answer for your angle theta is going to be 25.11 degrees. So that's the first thing that you need to know. And if I want to find angle alpha from here, clearly alpha is equal to arctangent of 0.8, which is about 38.66 degrees. Okay, so let me write it, although we don't need to use it in this problem directly, but it's good to just know that. Although the angle that you really want to go is 38 degrees with respect to the ground, but with respect to the water, you should shoot for angle smaller than that, 25 degrees. So when you add that 3 meters of water with respect to the ground to it, that can ultimately make it right. So that was the first part, that in which direction the angle of 25.11 degrees. And then the second part is, now how long does it take for you to do this crossing? For that, you need to bring that theta that you just found back into either equation 1 or 2. So let's say I bring it back to this equation 1. So this is 5.11, and this guy is basically that 3866. And if you do that, then that should give you VBG. So if I solve for VBG, velocity of boat with respect to the ground, I can find it. And if I do so, that is going to be basically 11.6 meters per second. Now, why is that important? Because this is the speed using which you travel the distance from point C to point D with respect to the ground. Because your goal is to go from C to D. So you need to travel this distance from C to D. This is with respect to the ground, and that VBG is also your speed with respect to the ground. So you have to divide that distance by that speed, and assuming that is constant, so that gives. The third problem is about kinetics of a particle, and here it is moving on a circular arc again with radius of 4 feet. And initially, when the angle theta is 0, where it's right down here, you give it an initial kick, you give it a move to the right, you give it an initial V naught of 14 feet per second to the right, and it causes it to go up. And here the surface is smooth, so there is no friction. It goes up, and how far it goes, that's not what this question is asking. The question is asking when it reaches a 60-degree angle, maybe somewhere here, then you want to find what? So this angle is 60 degrees. Then you want to find basically the velocity of the particle. So this is V2 that you don't know. V1 is the same as V0, which is 14. and the surface is smooth, there is no friction, and you have to use the Newton method, not work energy. If you use work energy here, it is much simpler. Okay, but here it is specifically asking you to use Newton method, and the weight of the block is 1 pound. So here this 1 pound is m times g. Okay, so here you have to use a coordinate frame, and it is suggesting to use the polar coordinate. Why? Because you have this angle theta and here this constant radius r. So here we're going to do that, and we're going to draw the free body diagram. Now, when you do the free body diagram, be very careful. You have to draw it somewhere between position 1 and position 2 at arbitrary angle. Do not draw it right in the beginning or at the end. So here we assume that this normal line is going to go through angle theta. And of course, the forces on this object are mg downward and the normal force in this direction. If there was a friction, that would be downward perpendicular to n. But here that's all you have, and then it is asking you to use our theta coordinate. So you have e theta in this direction and er radially out like that. And this angle is also theta. So that's your free body diagram and your coordinate frame, and now your goal is to use the Newton method in polar coordinates and find the speed of the particle when it's at 60-degree angle up. So here we have to use the equations of motion, right, in our theta coordinate, and remember that some force in the r and some force in the theta direction are equal to. But before I write they are equal to what, we have to first find them. So let's decompose them. Clearly, if you look, mg has an r component, and so this one is going to be mg times cosine of theta, and it has a sine component but in the negative e theta direction. So it is going to be mg times sine theta with a negative sign. Let me add that here. And n is in the negative r direction, so like this. These two are equal to what? So this is equal to mass times acceleration radial, and acceleration radial, if you remember, it is r double dot minus r theta dot squared. And this is mass times acceleration theta, which is r theta double dot plus 2r dot theta dot, right? The Coriolis acceleration. So what you need to find are basically these components. In this case, r is 4 feet, and that is constant, right? So r is equal to 4, and that is constant. What does it mean? It means that your r dot is 0, and that means your r double dot is 0. Of course, they have units, but that here makes life a little bit simple for us. So these two terms will be taken care of. Okay. Now, n is an unknown in these two equations, if I call them equation 1 and 2. And theta of t, in general, the way that this angle changes is, and all of its derivatives are unknown. Okay, so really you have two unknowns, theta of t and n. And equation 1 is good and useful when you are after n, if you want to know the normal force at any point. Otherwise, that does not give you a differential equation to solve, but equation 2 does. If you look at equation 2 and get rid of m in equation 2, then clearly equation 2, if you look at it, what kind of equation is that? If you look, it's r theta double dot equals negative g sine theta. So this is going to be theta double dot equals negative g over r times sine of theta. which is a second order differential equation. And of course, it has two initial conditions. What are those? The conditions are at t of 0, you can say theta is 0, and at t of 0, theta dot is a number that we can find through this v1. Okay, so we have two initial conditions. By the way, this is there is no analytic solution to this, as you know. This is like the pendulum equation, and it has to be solved numerically, but you need to solve it numerically if your goal is to find theta of t. But here we don't care about theta of t, right? We do not care about that. We want to know at the specific thetas, right, at theta 0, you have theta 1 dot, which I'll show you how to find it. At theta 2 of 60 degrees, what is v2 or what is theta 2 dot? So what you need to find is theta dot or omega at the specific theta. Nobody here cares about time. So the way to handle this is to write this theta double dot in its time independent format, or use the chain rule. So you write it as, this is basically d theta over dt, but using chain rule, you write it as d theta dot over d theta times d theta over dt. And guess what? This second one is theta dot, so you write it as theta dot d of theta dot over d theta. You see, you wrote your acceleration as omega d omega over d theta. There is no time in it, so this is the time independent version of theta double dot. Now this is equal to negative g over r times sine theta. Now if you look at this, clearly you can do separation of variables by simply multiplying both sides by a d theta. If you multiply both sides by a d theta, then you'll get this. Now if you look at this clearly on both sides, you are going to what? You are going to have a single variable. On this left side you have theta dot, on the right side you have theta, and you can integrate. This goes from theta of 0 to theta of 60 degrees, or pi over 3. This goes from initial theta dot 1 to the final theta dot 2. The question is, how do we find theta dots? And the answer is, what is the formula for velocity in the r theta coordinate, in the cylindrical or in polar? If you remember, v in general is r dot er plus r theta dot e theta. Right? But guess what? In this case, r does not change, so this component goes away, right? And there is no z, so clearly the magnitude of the velocity, the speed, v, is simply equal to what? The transverse component, r theta dot, which is the same as the circular formula, the circular motion formula. V equals r omega, or r theta dot. So if I want theta 1 dot, all I need to do is to divide v1 by r, right? So I just divide this v1 by r. So I divide that 14 by 4, and I get 3.5 radians per second. Okay, and theta 2 dot is the one I need to find. So this limit here is 3.5 to theta 2 dot. And integral of theta dot is theta dot squared over 2. So you have to calculate it at theta dot 2 and 3.5 and subtract. And integral of sine theta is negative cosine theta, but there is another negative. So this is g over r times cosine theta. And calculated at pi over 3 and 0. And everything is known except for theta 2 dot. If you solve for theta 2 dot, the number you are going to find is 2.05 radians per second. And once you have that, you're going to come back here, and clearly V2 is what? V2 is R times theta 2 dot. So that 2.05 you multiply by a 4, and you're going to get what? 8.2 feet per second. Done. That is your final answer. So you go from initial speed of 14 to what? To basically 8.2. You're going to reduce the speed, and it's obvious because during this travel, although N does not do any work on the system, but mg does, and it's a negative work, so you're going to lose some kinetic energy or momentum. So that is how you solve this problem with what? With the Newton method. Clearly, you have to get equation 2, and then you have to use time independent and do everything. And again, if you find theta or theta dot at any point, then you can, of course, what? You can find N. So for instance, like it can say at 60-degree angle, how much is the normal force? Then you plug in the theta dot that you just found in equation 1, as well as the 60-degree for cosine theta. That gives you the normal force at that point. Okay, so you can do that. Now, this problem could have been solved with work energy a lot faster and a lot easier. And all you had to do was to use the work energy equation, which is the total work done between position 1 and 2, which in this case is the work done by the normal force plus the work done by mg, because those are the only two forces acting on the object, is equal to 1/2 times mass times v2 squared minus v1 squared. And remember that normal force is perpendicular to the direction of motion, so that doesn't do any work. The work of mg is negative mg delta y, right? That's the formula that you learned. v1 is given, v2 is to be found. The only thing you needed to find was delta y of the object as it goes from theta 0 to theta 60 degrees. So if I go back and show you, basically all you needed to find was this change in the elevation from here to here. If you had this delta y, that would have been done. And you know, if you go from theta 0 to a specific theta for that radius, it's not very hard to find it, is it, right? Because if this angle is theta and that is r, this distance is r cosine theta, and this initial whole distance is r, so delta y is clearly r minus r cosine theta. Okay, so that's all you needed to do here, is to say that this delta y is 4 minus 4 times cosine of 60 degrees. And if you solve for v2, guess what? You're going to get exactly that 8.2 that we just solved for. So you see here, work energy is going to make life extremely easier and faster as opposed to the Newton method. But if in an exam somebody is asking you to use the Newton method as opposed to work energy, you have to follow the instructions of the problem. Okay? Let's go for the next one. Okay, the next problem, again, particle kinetics, but again, you can solve it with Newton method or work energy method. And I'm going to show you the Newton method, which is a little bit more interesting, or probably a little bit harder because you have to solve a differential equation. But you can also do work energy, no big deal. So here is a skydiver and his parachute. If you combine them into a particle, their total weight is 200 pounds. Again, you see its weight, mg. And he's falling vertically at 100 feet per second when he opens the parachute. As a result of that, he's going to experience a drag force of 0.5 v squared. You want to know the magnitude of the skydiver's acceleration right when it opens, and also the speed or the velocity, magnitude of velocity of it when he falls 20 feet from the point that the parachute opens. Okay, yes. So, and why would you care about the acceleration of the person? Because guess what? That acceleration is very important for the pressure that the internal organs of the person is going to experience. Okay, if that is a big acceleration, something like g or several times g, you're gonna feel a lot of pressure on your organs. You might even basically lose conscience and faint, right? And so much that you can see in pilots and fighter pilots. And this speed is also important, especially as it gets close to the ground and he reaches the terminal velocity. You want to make sure that he does not hit the ground with a huge speed and get hurt. So these numbers are important. Now let's take a look here. So the first thing is, as always, to draw the free body diagram. So if I represent both of these people, actually it's already in the air, so I can draw the free body diagram right on the object, right? So this is the mg of the system, and of course there is the air drag, ft. And here I'm going to use just a y-axis upward, because that's a rectilinear motion on a single line. And so if I write some of the equations along some of the forces along y, clearly this is Fd minus mg, right? And this is equal to m times ay, or y double dots, which is your acceleration, right? And here the drag force is clearly, based on what the problem says, is 0.5 times v, and v here is y dot, so it's simply y dot squared. And if you look here, clearly this is a second order differential equation, right? And it's nonlinear because of the drag term. This mg is constant. And here, the first thing that the problem is asking is the magnitude of y double dot at any point. So if you want y double dot from here for part A, you just divide both sides by m, and you get negative g here, and then plus 0.5 divided by m times y dot squared. And so all you need is to find basically the y dot at any point. Now it is talking about right when he opens the parachute, when that number is 100. So all you need to do is to just plug in 100 here, and G is 32.2 in this British system, and M is of course that 200 divided by 32.2. So if you plug in the numbers and find that, you are going to get basically 24 G's, which is about 772.08 feet per second squared. And that is a big number. Okay, so initially when that parachute is opened, the person is going to experience a huge deceleration, okay, a huge one. And clearly you see it's upward. This is a positive number, it's upward. So you're going down, but your acceleration is up, which means deceleration. So you're going to get a huge sudden change in the speed. That's for part A. For part B, you want to find the magnitude of velocity when you've gone down 20 feet. And again, it's about the change in velocity and displacement. Nobody cares about time. So the best way to handle it is to write this y double dot in a time independent formula, which is y dot dy dot over dy, v dv over ds, right? Okay, you can write it this way. And now this is equal to basically, as I said, 0.5 over m y dot squared, and then minus g. And now what you can do is to basically go ahead and divide both sides by this guy here. If you do so, here you get y dot over, and here 0.5 over m y dot squared minus g dy dot, and this is equal to dy, and multiply both sides by dy. And now look, both sides are separate variables, so you can do separation of variables, right? And in order for that to happen, you need to also um, do integrations to get the numbers. I mean, you have to do the integrations and put the limits. So this y goes from 0 to 20 because you are dropping by 20 feet. The only thing is, since y is upward, if the initial position is 0, the next position is not positive 20, it's negative 20. So be careful about the limits here and their signs. And y dot goes from the initial number, that is, and these are just magnitudes, so this is 100, and clearly this y dot number 2 is the unknown here. And clearly, if you look at this, the derivative of y dot squared is 2y dot. So if you multiplied this by 1 over m, which is 2 times 0.5 over m, that is exactly the derivative of denominator. So you can multiply by m and multiply by 1 over m. And now this here is clearly, this integral is a natural logarithm. So it is going to be m times natural logarithm of 0.5 m over m y dot squared minus g. This is calculated at y dot 2 minus calculated as 100. And the other side is simply going to be y calculated at negative 20 and 0. And from here, you should be able to calculate y dot number 2, which is going to be 28 feet per second. And it has to be less than the initial one of 100 because the parachute is going to slow you down. Okay, so clearly you see that you can easily use Newton method to solve this problem. And again, you could have done it with work energy. In this case, the drag force and the mg both will do work. The problem is for mg, the formula for work is negative mg delta y, but for the drag force is not constant. So in order to calculate the work of that, you have to do integration. You have to integrate that 0.5 v squared over dy. So the work of that is 0.5 y dot squared with a negative sign dy, and that is basically integral of y dot versus y. So you have to divide by a dt, multiply by a dt, so we can do it. So in this case, actually, although it might not look so obvious in the beginning, in this case, actually, the Newton method might be a little bit easier to handle the problem. Okay, let's go to the last problem. So here we have a sorting machine, let's say the one that they have in the airports, right? Of course, you know how they handle your luggage in the airport. They just threw them off of the airplane, right? That's how you get a broken luggage each time that you go to travel. So here they are trying to be very nice, and this parcel basically moves down from this slide that is 3 feet high. Initially, when it reaches there, due to the speed of this conveyor system behind it, it has the speed of 2 feet per second. It slides down the ramp, and the ramp is smooth, so assume that the effect of friction on this ramp is minimal. And of course, when it comes down here, it is going to have even a bigger speed because the gravity helped it gain momentum. And so now whatever this speed is, when it comes and hits this spring, you want to bring it to rest by this linear spring. And linear spring means the force of it versus the displacement is a linear function. Now you want to know what should be the spring constant. So in this case, this k is unknown, such that the 10-pound parcel, so here the weight of that parcel mg is 10 pounds, assuming, although you know you can go up to 50 pounds in international flights or something, that will not be subjected to a maximum deceleration greater than 10g. So when it goes through hitting the spring and comes to rest, it is going to go through deceleration. You don't want that magnitude of deceleration anywhere to be bigger than 10g. How much should be the spring constant such that the deceleration in it does not go beyond something, and that means you don't damage the contents of this luggage. Okay? Yeah. So, or parcel, whatever you might want to call it. So this problem has two parts. When you go from this position 1 to position 2, and then when you go from position 2 to position 3. Between 1 and 2, mg is working. Between 2 and 3, the spring is working. If you directly go from 1 to 3 and you don't consider that the weight was doing something, right, you might easily neglect the work of mg, and all you need to focus on then is the work of a spring, which is wrong. So it's better to break it into two parts, from 1 to 2 and then 2 to 3, and look at them individually using the work energy here, which is the problem is considering. Although you can use Newton method too, but work energy is way easier and more useful. Between 1 and 2, clearly, if you draw a free body diagram for an arbitrary point, you have mg and you have n. There is no friction in this case. And clearly between 1 and 2, n is normal to the path. mg is the only one doing work. So between 1 and 2, w of 1, 2 is simply w12 of mg. This is equal to k2 minus k1, which is 1/2 m times v2 squared minus v1 squared. And clearly v1 is given, that is 2, v2 is to be found, and m is also basically 10 pounds force divided by 32.2. And w of mg, as you know, this is negative mg delta y. Now one good thing here is on both sides there is m. So you can get rid of that m and not even bother to calculate it. Just know that this g is 32.2, and delta y in this case is 3 feet downward, so this is negative 3. Those two negatives would cancel. You get a positive work, which makes your v2 to be bigger than v1. So if you solve for v2, you can get your number for v2. Let's go ahead and calculate this number. So you will get 14.04 feet per second. This is how fast the object is moving down the ramp here. Now, when you go from 2 to 3, and 3, let's say, is the end of the stop, it's the rest. So here you have to draw the free body diagram when it comes into contact with the spring to include the force of the spring. And in this case, the forces are mg again, a normal force again, and the spring force this way. mg and n between 2 and 3 will do no work because they are both perpendicular to this horizontal motion. Because work of mg, remember, is negative mg delta y, but 2 and 3 are at the same y level, so there is no work. The only work between 2 and 3 is the work of a spring. So between 2 and 3, you can say w between 2 and 3 is only due to spring force, and this is equal to 1/2 times m times v3 squared minus v2 squared. Now in this case, v2 is known. v3 has to be 0 because you come to rest, and the work for a spring is negative k over 2 s2 squared minus s1 squared, where s here is the deflection at, and in this case actually it's 3 and 2, not 2 and 1. So in position 2, when the object is here at the bottom of the ramp, there is no deflection. The spring is completely at rest. So S2 is clearly 0. But S3, how would you find it? Okay, this is not known. So from here, if you solve and get rid of these 1/2 and maybe that negatives, you can see that k times s3 squared is equal to what? Is equal to m times v2 squared, which is basically a single number. This is just a number. I call it equation 1. Okay, if you want, we can get the number for you. So let's get the number. So this is equal, remember m was what? M was 10 divided by 32.2, and we multiplied by that v2 squared. So let's go ahead and do that. So you're going to get 6124. 6124 is this guy. That I call equation 1. Equation 1 has two unknowns, k and s3. So you cannot solve for that. But the problem has another thing that it is asking, and that is the maximum deceleration. So for that, I need to use the Newton equation in the x direction as well, right, in the direction of motion. So if this is the x-axis in this case, and you might say, why don't you do it right? I can, but if I do it to the left, then the spring force is negative. That gives me deceleration. If I do it to the right, the spring force will give me positive acceleration, but since basically the motion is to the left, that's the same thing. That's the meaning of deceleration. So it doesn't matter which one you do. And here, I'm going to go and write the equation of motion. So some force in the x direction is negative spring force. And the spring force, as you know, is negative k times s in general. This is equal to what? This is equal to mass times acceleration. Now this x double dot here has a limit. This guy has to be less than or equal 10 times g. Clearly you see that it's going to be negative. K is unknown, and s, let's talk about it. This is the maximum of deceleration or acceleration, that is 10g. Okay? Yes? So the maximum of that acceleration or deceleration is 10g, and in an equation, when the right-hand side becomes maximum, because m is constant, when acceleration or deceleration becomes maximum, the only way for that to happen is the left-hand side becomes maximum. And k is a constant number, it cannot change. So the only way is that this s becomes maximum. Okay, and S maximum happens when? Happens when the spring is at the very end at S3, when it's at the maximum possible deflection. So from here, you can clearly see that basically, if you're talking about magnitude of that, right? If you're talking about, magnitude of this guy should be less than 10g, then you can say that k times s3 should also be equal to what? 10 times m times g, and mg is 10 here, so that is going to be 100. And that is equation 2, which again you can find between these two unknowns. So now if you look at 1 and 2, guess what? Equations 1 and 2 are two equations, two unknowns, and the one that you care about is k. So in order to get rid of s, what you need to do is to square both of these equations. If you do so, right, let's see, this one starts working, there we go. So first I square equation 2, and then divided by equation 1, the s3 squared would cancel, you get an extra k, and that should, right, that should give you k. And the number that you can find for k is going to be 163 0.29 pound force per feet. Done. Okay, so here is how you solve for this fifth problem. So hopefully going through these 5 different problems for particle kinetics and kinematics helped you prepare for your upcoming exam, whether you are in my class or not, wherever around the world that you are. Hopefully it helped you. And later on, in probably a few weeks, since my students are going to have a final exam and that is going to be on rigid bodies, I'm going to probably make a similar video, but this time I'm going to solve rigid body problems, and I post it on my channel so you can also look at it. Thank you so much for your attention. I'll see you in the future.